Hi everyone. In this video, we're going to talk about eigenvectors. Now, we've been looking at linear transformations, and these things are given by matrices, and the structure of linear transformations starts to look more and more complicated as you look at all the possibilities of what can happen. So eigenvectors are a way of trying to bring some order to that chaos and trying to understand the structure of what linear transformations might do and make it look a little bit simpler. So I want to start off by working through a nice example. So let's consider the following matrix. Okay, so this matrix, it looks almost like the identity matrix, except I've got ones on the anti-diagonal instead of the diagonal. This is a 2 by 2 matrix, so it represents a linear transformation that goes from R2 to R2. And what does this transformation do? Well, it takes the vector 1, 0, and it sends it to the first column of this matrix, which is 0, 1. So this vector gets sent up to here, 0, 1. And it takes the second standard basis vector, 0, 1, and it sends it to the second column of this matrix, which is 1, 0. So it swaps these two. So if you think about it, this is going to turn out to be reflection across this line. So this is a linear transformation, and it's determined by what it does to the standard basis vectors. But it's also determined by what it does to any particular basis. And the standard basis might not have been the easiest basis to work with. So let's try a different basis. The basis I'm going to try here is v1 is going to be 1, 1. And that's a vector of length square root of 2, so I'm going to divide by the square root of 2 to make that into a unit length vector. And v2 is going to be the vector 1 minus 1, and again, I'll divide by the square root of 2 to make it into a unit length vector. So here is a new basis. What does this basis look like? Well, my vector v1 points out like that, and my vector v2 points down here. So this is v1, and this is v2. Now, how do I know this is a basis? Well, in 2 dimensions, it's easy. There are only 2 possibilities. Either the vectors are linearly dependent, in which case we can write one as a scalar multiple of the other, but obviously that's not true here. So the only other possibility is that the vectors are linearly independent. If we have 2 independent vectors inside R2, which is 2-dimensional, then those 2 independent vectors have to actually span the whole of R2. 2 independent vectors span a 2-dimensional space, and the only 2-dimensional space inside of R2 is the whole of R2. You can't fit something of dimension 2 inside something of dimension 2 without filling out the whole thing. The same goes for any dimension. You can't fit an n-dimensional space inside Rn without that subspace being the whole thing. So here's our new basis. And let's think about what this linear transformation corresponding to this matrix A does in this new basis. So in this basis, the linear transformation associated to this matrix A, it sends this vector v1. So v1 is along the line of the axis that we're reflecting along. So it sends v1 to itself. It fixes that vector. It doesn't move it. So that vector stays unchanged. And v2 is sent to minus v2. OK, so I just worked this out geometrically. If you want, you could instead calculate this by doing a times each of these vectors. So let's check at least one of these. A times v1 is equal to 0, 1, 1, 0 times 1 over square root of 2, 1 over square root of 2. So this is my vector v1 here. And when I multiply this out, I will get, for the first component, 1 over square root of 2, and for the second component, 1 over square root of 2. Okay, so this is what this linear transformation does. We could do the calculation for v2 and find this, or I worked it out using the geometric description as this map being a reflection. So let me just expand this out a little bit more. This is taking it's taking the v1 vector and sending it to 1 times the v1 vector plus 0 times the v2 vector. And this I can write as 0 times the v1 vector plus a minus 1 times the v2 vector. So if I were to think of this as a matrix describing what this transformation does in this v basis, the matrix would be, well, I look at the v1 vector, the first basis vector, and it's sent to a linear combination of the v's. So I read off those coefficients and I put them as the first column, 1, 0. So that's 1, 0. And then I look at the second column and I read off the coefficients of the v's for what this transformation does to the second vector. So I get a 0, minus 1. Right. So in this basis, this linear transformation has a very nice, simple form. It also had a fairly simple form in the other basis, so we haven't gained any simplicity in this particular case, except for the fact that in this standard basis, I had to think a little bit. I had to draw the picture to see that it's a reflection, whereas here, it's immediately obvious. In this basis, we see that one basis vector is fixed, it's unchanged, and the other basis vector is negated. So we're doing a reflection of the second axis across the line spanned by the first axis. So it's immediately obvious in the v basis that this is a reflection across the v1 axis. Now, one thing I want to point out here is that in this v basis, we had something very nice going on. We had that this linear transformation takes each of the v basis vectors, v1 and v2, and what it does is simply take that vector and scale it by some scalar. v1 gets scaled by a very simple scalar, 1, and v2 gets scaled by a slightly less simple scalar, minus 1. So each basis vector is sent to a scalar multiple of itself, and not some complicated linear combination of all the v's. So this is a very special phenomenon, and this leads us to the following definition. If we have a matrix which is n by n, and we have some vector v, which is sitting inside, say, Rn, we say that this vector is an eigenvector. Eigen is the German word meaning self, or own, as in one's own, oneself. So an eigenvector is a kind of self vector. V is an eigenvector of this matrix A. If there is some scalar, lambda, some number, such that this matrix times this vector, which is the same thing, recall, as the associated linear transformation function acting on this vector. So we take v as input, and we multiply it by the matrix A, and that gives us an output vector. And since this is an n by n matrix, the output is the same size as the input. So we can compare the output to the input. And if the output is a scalar multiple of the input, then we say that that particular v is an eigenvector. So an eigenvector is one where A times that vector is a scalar multiple of that vector. And now you look back and see that what we had in this example here was v1 is an eigenvector with eigenvalue 1, and v2 is an eigenvector with eigenvalue minus 1. This number lambda, the scalar that appears in this equation here, is the associated eigenvalue. Okay, so finding eigenvectors is a very useful thing to do, and we'll see this in some examples. It tells us lots of information about the structure of the matrix and the associated linear transformation. Right. So let's have a look at how we actually find an eigenvector for a matrix. So if you want to find the eigenvectors, the trick is, the first step is find the eigenvalues. So we are looking at the equation A times V equals lambda times V. And at the moment, both the vector V, that's going to be the eigenvector, and the scalar lambda are unknown. So we've given a matrix, and that's all here. We need to find a scalar, and we need to find a vector. If we had a lambda and a v that solved this equation, then I could move this right-hand side vector over to the left-hand side and write av minus lambda v is equal to the 0 vector. And now I can do a little bit of factorization here. I can rewrite this as a minus, now I can't subtract a scalar from a matrix, but if I multiply the scalar by the identity matrix, then I can do the subtraction, and if you multiply this out, this makes sense. The identity, this is an n by n matrix, so this is the n by n identity matrix, which means 1's down the diagonal and 0's everywhere else. So the identity matrix times v is just v. So lambda times the identity times v is just lambda times v. So that gives us this term, and a times v gives us this term, the first term there. Okay, so we're looking for a solution to this equation. Now this is saying that lambda is some number such that this matrix has a kernel, and v is sitting inside the kernel. Remember, the kernel is the set of all vectors that are sent to 0 by some linear transformation, by some matrix. So to say that we have a lambda and a v such that this is equal to 0 says this matrix has a kernel, and v is some vector in that kernel. So the first step is we need to make sure that this matrix has a kernel. Right? Now this is a square matrix, so it has a kernel if and only if the determinant is 0. This condition that the determinant is 0 is the same thing as saying that this matrix here is singular. A singular matrix is one where the kernel is non-zero, where the determinant is 0. Okay, so we need to find a lambda so that this matrix is singular, and then we need to find a v in the kernel. So step 1 is find a lambda so that the determinant here is 0. And then step 2 is find a v in the kernel of this linear transformation, that matrix. So those are the 2 steps that we need to carry out. Let's look at the first step, finding a lambda so that the determinant is 0. So a minus lambda I times the n by n identity. This is an n by n matrix. So we can take its determinant. We've got n copies of lambda down the diagonal here. So when we take the determinant of this thing, we get a polynomial of degree n in this variable lambda. So this will be something of the form lambda to the n plus some constant c1 times lambda to the n minus 1 plus c2 lambda to the n minus 2 plus dot 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 all the way down to cn times lambda to the 0, so that's just 1. Okay, so this is what the determinant looks like. This c1 up to cn are a bunch of real numbers if we're dealing with a real matrix, or maybe they're complex numbers if we're dealing with a complex matrix. Okay, this is a degree n polynomial, so it has n complex roots. Some of those roots might be repeated. For instance, if you have just lambda to the n equals 0, then that has that has 0 as a root of multiplicity n. If you have lambda minus 1 to the nth power, then that has 1 as a root of multiplicity n. So we'll have n different roots if we count them with their multiplicities, and we're allowed to use complex numbers. If we're only using real numbers, then you might see fewer than n roots. But we'll have at most n roots and possibly fewer, and some of them might be repeated. And you only can get n if you count the roots with their multiplicities, and you're only guaranteed to get n if you use complex numbers. So you find the roots to this polynomial. And let's call these roots lambda 1 up to lambda k. And now for each of these, let's call it lambda I. we're going to solve the equation A minus that chosen critical value, this lambda I, times the n by n identity matrix, times some vector x equals the 0 vector. So we're looking for some unknown vector x, which sits inside the kernel of this square matrix here, and we've chosen this value lambda I to make sure that there is, in fact, a non-trivial kernel. There is some non-zero solution to this equation. You can always take x to be the 0 vector, so that solution is always there. What we're interested in are the non-zero solutions. So we need to try to solve this. To solve this system of linear equations, you take this matrix, and you could say, well, to solve a system of equations, I just need to multiply by the inverse of this matrix. Except that doesn't work here because this matrix is not invertible, because we've explicitly made sure that this matrix has a determinant of 0. So this matrix is not invertible, but we still need to find a solution. And what's going to happen is when you write out the equations and do your usual pattern of eliminating variables and trying to solve, you'll find that there's a little bit of freedom here, and you'll have at least a one-dimensional, or possibly 2 or 3 or more dimensions. You'll have some positive dimensional space of solutions. And if you're doing this on the computer, then the computer can calculate for you a basis for the space of solutions to this equation. So it's helpful to see an example of this in action. So let's clear the board and work through an example. OK, let's go through some examples. So first example is, let's take A to be this matrix that we saw before, 0, 1, 1, 0. So this is reflection across that diagonal line, y equals x. So if I write out A minus lambda 2 by 2 identity here, then this is minus lambda 1, 1, and minus lambda. And the determinant of this thing is equal to the upper left times the lower right minus the product of the other two. So I get minus lambda times minus lambda. That's the product of the two on the main diagonal minus the product of the two off-diagonal entries. 1 times 1. So this is lambda squared minus 1. And the roots, the values of lambda that make this equal to 0, are both 1. So I've got two roots. I've got 1 is a repeated root. So I've got an eigenvalue of 1. That's our only eigenvalue in this case. Now we need to plug in lambda equals 1. So A minus 1 times the 2 by 2 identity. This is equal to the matrix minus 1, 1, 1, and minus 1. And now I need to find the kernel of this matrix, or I need to find some vectors in the kernel. So remember, the kernel is the set of all vectors that give me a 0 as output. One way to think about that is the kernel is all of the linear combinations of the columns that give me the 0 vector. It's all the linear relations between the columns. And in this case, I can see that the second column is minus the first column. So the only linear relation that we have is that the second column is the negative of the first column. That's the only linear relation, and that gives us everything else. So that tells me that the vector take 1 from the first column plus 1 from the second column, or sorry, 1 times the first column plus 1 times the second column. This vector will be in the kernel. Right, so this matrix times this vector gives me the 0 vector, and any multiple of this also gives me the 0 vector, and that's everything that we can find in the kernel. Right. Saying that this is in the kernel tells me the kernel is at least one-dimensional. If the kernel were two-dimensional, then the kernel would have to be everything, and the only matrix that has absolutely everything in the kernel is the 0 matrix, and this is not the 0 matrix. So I can tell that the kernel can't be two-dimensional. It has to be one-dimensional, so we found a basis for the kernel. Okay, so we found a vector in the kernel, so that tells us that the vector 1, 1 is an eigenvector with eigenvalue 1. I forgot one of the roots here. So plus 1 is a root, and minus 1 is the other root. Forgot about that. The minus 1 squared also gives me a 1. OK, so let's try what happens when I use lambda equals minus 1. So let's try a minus 1 times the 2 by 2 identity. In this case, we have now the vector, let's see, minus lambda gives me a plus 1, a 1, and a plus 1. And now the only linear relation that I have is that the second column is equal to the first column. So the first column minus the second column is 0. So 1 minus 1 is in the kernel. And this is a basis for the kernel. So we have that 1 minus 1 is the eigenvector with eigenvalue minus 1. OK, we've found two eigenvectors, and they have eigenvalues plus 1 and minus 1. And this now completely describes this matrix. If we work with respect to this basis, then we saw that you can write this matrix in this very nice form where we just put the eigenvalues on the diagonal of the matrix, a 1 and a minus 1. This also tells us in this basis immediately what the matrix is doing. So this is an eigenvector with eigenvalue 1. So anything along the line spanned by this, anything along this line, so there's my point 1, 1, is unchanged. It's fixed by this transformation. And anything along the line spanned by this vector, 1 minus 1, so that's down here, is reflected across to there. The eigenvalue is minus 1. So that completely describes this linear transformation. And in this basis of eigenvectors, it's immediately clear that this is indeed a reflection. So the idea is the eigenvectors can help us see geometrically what the linear transformation is doing. After this video, the next video is going to be a little supplementary video. If you're happy with this material, you can skip the next video. If you want to see a few more examples, go ahead and watch. So the next one is just going to be a series of more examples working out eigenvectors and eigenvalues and what can happen. Thanks for listening. Hello, everyone. Having seen the definition and first example of eigenvectors and eigenvalues, it's time to work through a few more examples. So I consider this video supplementary. If you're happy with eigenvectors and eigenvalues and happy to let the computer crunch the numbers for you, then you can go ahead and skip this one. But you're welcome to watch and see a few examples of what can happen with calculating eigenvectors and eigenvalues. It might help you to understand some of the outputs that you can get from the computer a little bit better. So let's look at example 1 here. Our matrix is going to be a 2 by 2 matrix with a lot of 2's in it. So let's take this matrix and let's look at A minus lambda times the 2 by 2 identity. This is 2 minus lambda, 2 minus lambda, a 2 and a 2. The determinant of that thing is 2 minus lambda squared minus 2 squared is 4. OK, so if I multiply this out, this gives me lambda times 2 minus lambda. Oops, that's not right. That's what I get for trying to do it in my head. If I multiply this out, this gives me lambda times lambda minus 4. So the roots here, the solutions to this equals 0 are lambda equals 0 and lambda equals 4. Okay, so those are our two eigenvalues. Now let's look at each one of those in turn and find the corresponding eigenvector. So we'll do lambda equals 0 first. A minus 0 times the 2 by 2 identity is just A. So this is 2, 2, 2, 2. This one's going dry already.
Is that yellow?
Yeah. Okay, so this 2 by 2 matrix here, I see that the second column is equal to the first. So the any vector in the kernel is going to be spanned by the vector 1, minus 1. So this says however much I take of the first column, I need to take the same amount but negative of the second column to make the 0 vector. So, so we have 1 minus 1 is the eigenvector with eigenvalue 0. Okay, how about our other eigenvalue, 4? So in this case, A minus 4 times the 2 by 2 identity is equal to minus 2, 2, 2, and minus 2. Almost the same here. Now I see that the second column is minus 1 times the first. So however much of the first column I take, I need to take the same amount with the same sign of the second column to make the 0 vector. So in this case, the kernel is spanned by the vector 1, 1. So 1, 1 is the eigenvector. And the eigenvalue in this case is 4. Okay, example 2, let's take the matrix A to be 3, 3, and zeros off the diagonal. A minus lambda times the 2 by 2 identity matrix is equal to 3 minus lambda, 3 minus lambda, 0, 0. And when I take the determinant of this thing, I get 3 minus lambda squared minus 0. So the roots are, well, there's just one, and it's 3. So 3 is our eigenvalue. So we've only got one eigenvalue in this case, whereas in the previous one we had 2 eigenvalues. We've got one eigenvalue here. Let's look at what the kernel is now. So A minus 3 times the 2 by 2 identity is equal to, oh look, it's the 0 matrix. So the kernel is all of R2 in this case. So let's contrast these two cases. In case 1, we had 2 distinct eigenvalues, and each one we were able to find an eigenvector. So we had a basis of eigenvectors, 2 eigenvalues, 2 eigenvectors. In case 2, we had only a single eigenvalue, but we had a 2-dimensional space of eigenvectors for it. So everything is an eigenvector with eigenvalue 3. So in this case, we say that there is a 2-dimensional eigenspace. When you find an eigenvalue, the set of all eigenvectors for that eigenvalue is a linear subspace. So we call that the eigenspace. So in example 1, we had 2 eigenvalues, and each one had a 1-dimensional eigenspace. In example 2, we have 1 eigenvalue, but it has a 2-dimensional eigenspace. Let's look at another example to see some slightly different behavior. Here's example 3. Let's take the matrix, which is a 1, and let me put, say, some random number like an 8 in the upper right corner and a 0 in the lower left corner. Okay, so A minus lambda times the 2 by 2 identity matrix. This is 1 minus lambda, 8, and 0. And the determinant of this is equal to 1 minus lambda squared times 8 times 0, minus 8 times 0. So I just get 1 minus lambda squared minus 8 times 0. The roots of this are just, the only root here is lambda equals 1. That's the only root we have. Okay, so we found one eigenvalue, potentially. We need to find an eigenvector that goes with this. So let's look at A minus 1 times the 2 by 2 identity matrix. This is 0, 0, 8, 0. Okay, now in this case, any way of making the 0 vector out of these two columns has got to be, I can take as much as I want of the first column, and I can only take 0 times the second column because I've got this 8 there and I've got nothing in any of the other columns to cancel that 8. So the kernel is spanned by 1, 0. So this says any amount of the first column and 0 of the second column. Any vector in the kernel is a multiple of this, and that's all I can find in the kernel, multiples of this guy. By the reasoning before, if this says the kernel is at least 1-dimensional, and if the kernel were 2-dimensional, this matrix would have to be the 0 matrix. Okay, so we've found one eigenvector with eigenvalue 1. We found one eigenvector, but we can't find any more. So now we have one eigenvalue and a 1-dimensional eigenspace. So in the first two examples, we saw that we could find a basis of eigenvectors. Either we had 2 eigenvectors with distinct eigenvalues, or we had one eigenvalue, but it had a 2-dimensional eigenspace associated with it. And since we're in R2, whenever you find a 2-dimensional space, eigenspace, that has to be the whole thing. So in both of those cases, we had a basis of eigenvectors. But in this case, we found one eigenvalue and a 1-dimensional eigenspace and nothing more. So even though this is a linear transformation from R2 to R2, we've only got a 1-dimensional eigenspace, and we can't find a second eigenspace to fit with this. Let me do one more quick little example here, and this shows some interesting phenomena, which is you need to pay attention to real versus complex numbers. So let's consider the matrix A given by 0, 1, minus 1, 0. And if you work this out geometrically, let's see what's happening here. The first unit vector, 1, 0, is sent to up here. The first basis vector is sent to the second standard basis vector. And what about the second one? Well, this guy up here is sent to this one over here. Okay, so from this picture, you see that this frame here is being rotated by 90 degrees anti-clockwise. So that's the transformation we're looking at here. This is a 90-degree anti-clockwise rotation of the plane. Okay, thinking about this rotation, I don't see any way we could have an eigenvector. There's no eigenvector in the plane, because any vector is getting rotated to a perpendicular direction. So there's no way I could take a vector as input and find that a times that vector, so a 90-degree rotation of that vector, is a scalar multiple of that vector. There's no way that a vector and something orthogonal to it are both pointing in the same direction. So it looks like there are no eigenvectors. But let's look at what happens when I use complex numbers now. So let's consider 0, 1, minus 1, 0. And I'm going to multiply this by the following vector, 1 and I. So now I'm going to allow myself to use complex numbers. And this I here is that very special complex number, I squared is equal to minus 1. So we're adding the complex numbers into the game here. What happens when I do this multiplication? Well, I get a vector that is 0 times 1 minus I in the first component, 1 times 1, and 0 times I in the second component. So I get minus I, 1. And now, let's see what happens when I take this vector and multiply. Well, let me do it the other way around. Let me take this vector and multiply it by minus I. So minus I times 1I is equal to minus I in the top. And minus I times I, well, that's minus I squared. So I get a 1 there, which is this thing. So we've just checked that 1I is an eigenvector, and the eigenvalue is minus I. Okay, so we didn't see any eigenvectors in the real plane, but as soon as you go to the complex numbers, we found one eigenvector, and it's got a complex eigenvalue, and that eigenvector has complex entries in it. So let's look at the determinant, this thing called the characteristic polynomial, to see where this eigenvalue of minus I comes from, and if there's another one hanging around. So let's look at the determinant of A minus lambda times the 2 by 2 identity matrix. This is equal to the determinant of minus lambda, 1 and minus 1. This is equal to lambda squared. Minus 1 times minus 1 is plus 1. And the roots in this case are going to be plus I and minus I. So minus I was the one we found in that example there. And there's this other root, plus I, which is going to have another eigenvalue, there's this other root, plus I, which is going to have another eigenvector associated to it. So this minus I, we found a 1 and I was the eigenvector. And here, there's some other eigenvector. And I'll leave it to you if you're curious to work out what that eigenvector is. But this is a case where we can find a basis of eigenvectors as long as we allow ourselves to use the complex numbers instead of the real numbers. So that was my final example. Thank you for listening. Hello everyone, welcome. In this video, we're going to look a little bit more deeply at what happens when we switch from working in one basis to working in a different basis. So in the last couple of videos, we saw some of the utility of thinking about a linear transformation in terms of what it does to something like a basis of eigenvectors. And now we're going to look more closely at that process of switching from the standard basis to some particular basis that might make your transformation or the problem you're interested in a bit easier. So this is a big theme in linear algebra. Always try to work in an appropriate coordinate system, in an appropriate basis. Your life will be much easier. Computations for the computer will often go much faster if you're working in a situation where the computation time is getting to be significant. All of that will be better if you can switch to a good basis. So let's see what happens here. I want to start in good old Rn, our comfortable home. And we have now a couple of different bases here. We have what we've been calling the standard basis, and I think I'll call these in this video E1 up to En. So just to remind you, Ei is the vector which is all zeros, and then it's got a 1 in the ith position, and then all the rest zeros. So they start off 1 and then zeros. The second one is 0, 1, and then zeros, and so on. So this is the standard basis. And if I have some vector u, which I'll write as u1, u2, up to un, I can think of this as expressing a linear combination of the standard basis vectors. This is u1 times the first basis vector plus the number u2 times the second basis vector, and so on. Okay, so we've got that basis, and let's suppose that we have some other basis. Let's call it v1 up to vn. Now, an important fact in linear algebra called the invariance of dimension is that if you have one basis that has n vectors in it, then any other basis has to have the same number of vectors in it. So don't look for more or fewer vectors in some other basis. It's got to be exactly n. Now, in this basis, because this is a basis, I can take any vector u and write it uniquely as lambda 1 times v1 plus lambda 2 times v2 up to lambda n times vn. So the fact that there exists an n tuple, a sequence of numbers lambda 1 through lambda n, is the fact that these vectors span all of Rn. And the fact that they're unique is the fact that these vectors are linearly independent. So if they're linearly independent, that tells you that if there is one way to make some vector u, then there's only that one way. And the fact that they span all of Rn tells you that every vector can be made in at least one way. OK, so I can think of this vector u in terms of the standard basis given by listing off its components. Or I can think of this vector u as being represented by saying we're working in the v basis, and I'm going to give you this list of coefficients. So I'll write this as a column vector, lambda 1 all the way down to lambda n. And this list of coefficients represents this vector u in this basis given by the vi's, v1 up to vn. Now, given this basis, I can cook up a matrix. I'll call it P. This is going to be an n by n matrix. And what I'm going to do is take the first basis vector, v1, and stick it as the first column. I'm going to take the second basis vector, v2, and stick that as the second column, and so on. Vn is going to be the last column. So I'm making a column, I'm making a matrix where the columns are given by my basis vectors vi. If I did this with the standard basis vector, then what I would get is the identity matrix. But in this case, if these are not the standard basis, I get some other matrix. And the fact that these vi's are a basis is equivalent to this matrix P being invertible, which is equivalent to the determinant being non-zero. and also equivalent to the kernel being only the 0 vector. Now, what does this matrix do to the standard basis vectors? Well, this matrix times the standard basis vector EI. Well, P times the vector that has a 1 in the ith position and zeros everywhere else simply picks out the ith column of this matrix. So that gives me the ith vector of my new basis. So P sends each of my standard basis vectors to these new basis vectors. Now, I can reverse this if I have an inverse, and P is invertible, so I could say that EI is equal to P inverse times VI. So where did I get this equation from? I just took this equation and multiplied on the left by P inverse. So P inverse times P times EI. The P inverse P cancels out, and I'm left with EI is equal to P inverse times VI. So the P inverse matrix takes the V basis vectors and moves them all to the standard basis vectors. Now this is useful because if I take a vector u and I think of it as being represented by these lambdas, then I can write the following. So P times the vector lambda 1 up to lambda n is equal to lambda 1 times v1 plus lambda 2 times v2 plus dot 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 up to lambda n vn, which was my vector u that's represented in the v basis by these coefficients. So the matrix P takes the list of coefficients, the representation in the v basis, and converts it back to the standard basis. So this, if I write u here, I'm thinking of this as given this list of components here. So I've taken the representation in the v basis, and I've converted it to the representation in the standard basis. Matrix P takes as input the representation of a vector in the v basis, and the output is going to be a representation of that same vector in the standard basis. If I have u, which is given by u1 up to un, or it can be represented as lambda 1 times v1 plus dot dot dot, then this matrix P times lambda 1 up to lambda n is equal to u1 up to un. Now the inverse matrix does the opposite. It goes from the representation in the standard basis and gives us as output the representation in the v basis. So P times the vector of components of this vector u in the standard basis gives us, P inverse, gives us the representation, the coefficients in the v basis. So if I have a vector u and I want to know how to write it with respect to this basis of v's, I just multiply by this inverse matrix, P inverse, and that will tell me the coefficients that I need to use. Let's look at an example here. In this example, let's take the following. I'm going to look at the basis vectors v1 is 1, 1, and v2 is going to be 1, minus 1. Now, let's put these together into my matrix P. So this is v1 goes as the first column, 1, 1. v2 goes as the second column, 1, minus 1. And now, let's check what happens here, just to make sure that we've got this right. Before we check, I need to work out the inverse. So P inverse is equal to, I gave you the formula before, So if I have a matrix A, B, C, D, and I want to take the inverse, I need 1 over the determinant of this thing, which was AD minus BC. So that AD minus BC is the formula for the determinant, times the matrix where I put D there, and A there, and minus B there, and minus C there. OK, so let's use that formula on this matrix here. If you plug it all in, what we get is the determinant is a minus 2. So we get minus 1/2 times minus 1, minus 1, and then minus 1 and a 1. So this works out to be 1/2, 1/2, minus, oh, no, that's a plus there. The minus 1/2 goes there, plus 1/2. OK, so there's my inverse matrix. And let's just do a quick check. P inverse times the vector 1, 1. This should give me the first standard basis vector, right? P inverse is supposed to send my standard basis to the V basis. So V1 here, represented in the standard basis, is 1, 1. And P inverse is supposed to send that to the expression in the V basis, which should be 1 times V1 and 0 times V2, so 1, 0. Let's check that that's the case. So I need to multiply this out. So I have 1/2, 1/2, 1/2, and minus 1/2 times 1, 1. I get 1/2 times 1 plus 1/2 times 1, so I get a 1 there. And 1/2 times 1 minus 1/2 times 1, I get a 0. So if I take this vector v1 and represent it in the standard basis, then P inverse converts that into the representation in the V basis. So this is saying that this vector here, so 1, 1, which is a representation in the standard basis, is equal to 1, this one here, times v1 plus 0 times v2. That's what this vector is saying. OK, and we could do the same check for 1 minus 1, but I won't bother writing that out. And let's just do one more check on this diagram. Let's suppose I take v1 plus v2. So let's take this point here, which has coordinates in the standard basis, which are going to be 2, 0. And I've cooked that up so that this is supposed to be v1 plus v2. OK, so 2, 0 is supposed to be 1 times v1 plus 1 times v2. So the representation in the V basis is supposed to be 1, 1. So let's check that that's the case. So P inverse takes as input a representation in the standard basis. So we'll take this point, 2, 0. 2 times the x standard basis vector and 0 times the y standard basis vector. And let's multiply it out. So this is 1/2, 1/2. 1/2 and minus 1/2 times 2, 0. And we get 1/2 times 2 plus 1/2 times 0. So that's a 1. And 1/2 times 2 minus 1/2 times 0. So we get 1, 1. And this one corresponds to the fact that this v1 has a coefficient of 1. And this one corresponds to this v2 has a coefficient of 1 there. So it all checks out. OK, so given this basis of vectors v1 up to vn, we made this matrix P and its inverse. And those gave us a way of converting between representing a vector in the V basis versus representing it as a linear combination of the standard basis vectors. Now let's think about what we can do when we have a linear transformation. So let's suppose we have a matrix A, which is an M by N matrix. And I'm going to do this a little bit more generally here. So this corresponds to a linear transformation that takes as input an n-dimensional vector, and the output, the codomain here, is an m-dimensional vector. So this sends some vector u to simply A times u. So this is just matrix multiplication. Now, first, let's suppose that we have some non-trivial, some new basis for the domain. So let's suppose our basis for the domain is called v1 up to vn. This n has to match that n there. So we've got this new basis, and what can we do with it? Well, we can represent u in the standard basis, or we can represent it in this v basis. So let's think about trying to work out what this linear transformation does if I want to give it an input represented in the v basis instead of the standard basis. So let's take a vector u and write this as lambda 1 times v1 plus dot 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 up to lambda n times vn. So this vector lambda 1 up to lambda n is the representation of v, a representation of u in the vi basis. So let's see what we can, if we can work out a formula for this linear transformation if we want to give it this input in the v basis. So let's take this input here. And now the first thing I need to do is convert this into the standard basis. So I can send this to my vector u by multiplying by my matrix P. So P converts the v basis representation into the standard basis representation. Remember, P is the matrix that has these basis vectors as its columns. Now from here, I can multiply by this matrix A, and so this is doing my linear transformation f sub A, and f sub A is just multiplication by A. So we find out that the output of this linear transformation is given by taking an input represented in the v basis and multiplying by the matrix P, and then multiplying by the matrix A. So this composition here is given by sending this thing to multiply by P first, and then by A, and we're acting on lambda 1 up to lambda n. So AP takes as input a basis expressed in the v basis. It takes this list of coefficients. And first, the P converts that back to the standard basis representation, and then A does what it's supposed to do to the standard basis representation. And the output comes out of that as a vector in Rm expressed with respect to the standard basis of Rm. So we get just a list of the components, the m different components here. OK, so by sticking a P on the right-hand side of A, we've changed A so that instead of taking its input in the standard basis, it expects an input to be expressed in the v basis. What about changing the basis of the output? So let's suppose that we have a basis w1 up to wm. This is a basis of the codomain Rm, so the place where the output vectors are living. And we can make from this a matrix Q, which is going to have columns w1, w2, and so on. So this is now an m by m square matrix. And because this is a basis, this is invertible. And so we can write down its inverse. And so we can use these matrices to change between the standard basis representations of things in the output space and the W basis representations. So now Q inverse times A times P. This takes as input a representation in the V basis. P converts it to the standard basis. A does what it's supposed to do in the standard basis. And then Q inverse converts that representation in the standard basis of Rm to the representation in the W basis. So now if I want to give an input to this linear transformation f sub a, but I want to represent it as a linear combination of the v's, so I just want to list these lambdas and give that as my input. Then I take that lambda vector, I multiply it by p, multiply it by a, and then multiply it by q inverse, and I'll get a list of coefficients that I think of as coefficients for the w vectors. And so if we do u is equal to this thing, so I'm going to represent it by a lambda vector, lambda 1 up to lambda n, then q inverse a p times lambda 1 up to lambda n. This will be equal to some vector mu1 up to mu m, where a times my original vector u is equal to mu1 times w1 plus mu2 times the second basis vector in the w basis, and so on. So this is what I mean to express the output in the w basis. I'm giving the input in terms of its coefficients of the v basis vectors, and the output is the list of coefficients, the mu's, which I think of as being the coefficients of the w basis representation of the output. So this product of these three matrices gives me the linear transformation for A, except represented with respect to these two bases. Now we can also do this a little bit in reverse. So we can do the opposite. We can do the converse here. So suppose we have a matrix B, which is m by n. So this represents a linear transformation from Rn to Rm. But let's suppose that this matrix B represents a linear transformation with respect to the v and w bases. So what I mean by this is if I have a vector u, which is represented in the v basis by a bunch of lambdas, so it's lambda 1 times v1 plus dot dot dot. So I'm representing it as a vector like this. And then this linear transformation represented by b sends u to some vector which is mu1 times the first w basis vector plus dot dot dot. So I'm representing the output as mu1 down to mu m. So this matrix B is the matrix such that B times this vector of lambdas, lambda n, is equal to mu1 down to mu m. So that's what I mean to represent a linear transformation with respect to these two bases. So it takes as input a representation of a basis, a representation of a vector in the v basis, and it produces as output a representation of a vector but with respect to the w basis. Now I can do the reverse. I can take q, b, and p inverse. So the p inverse now will take a representation of a vector in the standard basis, convert it to a representation in the v basis, do b to that, and then q converts the output, which is a representation of the w basis, and converts it back to a representation in the standard basis. Right. So we started with the matrix B representing what happens to representations of vectors in these new bases, and we were able to convert back to a matrix which represents what this linear transformation does to vectors when we write them down with respect to the standard bases for the domain and codomain. Right. So let's see this in action with an example. So I'm going to go back to the same basis we had before, which was our vector v1 represented in the standard basis was 1, 1, and v2 represented in the standard basis is 1, minus 1. So our matrix P here was the matrix 1, 1, 1, minus 1. And our matrix P inverse, the inverse of this guy, was 1 half, 1 half, 1 half, and minus a half. OK, so this is the setup. And now we need to add into the mix here a linear transformation. And so let's define this linear transformation with respect to the input and the output being specified in the v basis. So let's say that this linear transformation f is going to go from R2 to R2. So I'm keeping things simple by using the same domain and codomain and specifying the input and the output with respect to the v basis. I'm going to say v1 is sent to, let's say, 4 times v1. So it scales the first v basis vector by a factor of 4. And v2, let's say it scales this by a factor of 3. OK, so here's a linear transformation. It's stretching things by a factor of 4 in this direction, and it's stretching things by a factor of 3 in this perpendicular direction. That defines a linear transformation, but what is the matrix for this in the standard basis? Well, the way I've defined this, representing the input and the output in the v basis, that was the second case that we just worked out. So our matrix B is going to be 4, 3, 0, 0. So this says it scales the first v basis vector by a factor of 4 and adds no amount of v2 to it. And it scales the second basis vector v2 by a factor of 3, and it adds no amount of v1 to it. So that's our matrix B. And now we need to use the formula that we just had. The formula was Q inverse, but our Q and our P are equal to each other in this case. So P inverse and Q inverse are the same. So it was P inverse times B times P. And this is the matrix we want. So let's write this out. So the formula that we want is the one that we just had. We want Q, B, P inverse, but Q is equal to P. So we want P, B, P inverse. And if we write this out, this is 1, 1, 1, minus 1 times 4, 0, 0, 3 times 1 half, 1 half, 1 half, and a minus 1 half. So let's multiply this out. If I multiply these two, I get the matrix 1 times 4 plus 1 times 0. So I get a 4 there, 1 times 0, and 1 times 3. So I get a 3 there. 1 times 4 and minus 1 times 0, I get a 4 there. And 1 times 0 minus 1 times 3, so I get a minus 3 there. So that's these two, and I multiply by this matrix here. So 4 times a half, that's 2 plus 3 halves. And then the next piece here is going to be 2 minus 3 halves. Down below this corner is going to be 2 minus 3 halves. And the final corner is 2 plus 3 halves. OK, and we can get a common denominator on these and write this as 7 halves, and then 2 minus 3/2 is 1/2. 2 minus 3/2 is 1/2. And 2 plus 3/2 is 7/2 again. Okay, so this is the representation of this linear transformation in this standard basis. So that example we just saw is a special case of a very general process called diagonalization. So let's suppose that we have a matrix D, and we're now going to be in a general number of dimensions. So let's suppose that this is what's called a diagonal matrix. It's got some entries lambda 1, lambda 2, down to lambda n on the diagonal, and everything off the diagonal is going to be 0. So this is an n by n matrix. I've got lambdas on the diagonal, so a bunch of numbers on the diagonal, and everything that's not on the diagonal is 0. So this is what we call a diagonal matrix. And a diagonal matrix has a special property. A diagonal matrix has eigenvectors given by the standard basis vectors, and the corresponding eigenvalues are the lambdas. So what I mean by this is D times the ith standard basis vector, which I've been calling EI, is going to be lambda I times EI. If you don't believe me, just multiply it out and check. Okay, so this is a matrix that has lots of eigenvectors and corresponding eigenvalues. And by choosing these lambdas, you can make the eigenvalues be whatever you want. And this is an example of a matrix where we have enough eigenspaces. The sum of the dimensions of the eigenspaces is the whole of our domain Rn here. Now, let's consider what happens if we want a matrix that has a bunch of eigenvalues, lambda 1 through lambda n, but the eigenvectors might be some different set of vectors. So let's take some arbitrary basis, v1 up to vn, and we make from this our matrix P, which had v1 as the first column, v2 as the second column, and so on. So let's now use the change of basis formula and look at the matrix P, D, P inverse. This matrix, I claim, has eigenvectors given by the v's. And the eigenvalues will be the same ones as we had before, the lambdas. So let's check this. P, D, P inverse times a vector vi is going to be equal to, well, if I do this first multiplication, P inverse converts from the standard basis to the v basis. So this converts the vector vi into the standard basis vector ei. It tells us that vi is a vector which, when written in terms of the v basis, has a coefficient of 1 in front of vi and coefficients of 0 in front of all the other v's. So that's the vector ei. D times ei is lambda I times ei. So this is equal to P, D, ei, and this bit here is lambda I times ei, because ei is an eigenvector with lambda I as its eigenvalue. And then P here is linear, so this is equal to lambda I times P times ei. I can pull this scalar lambda outside of the matrix multiplication. Matrix multiplication is linear. And then P converts from this converts from the v basis back to the standard basis. So it sends the ith standard basis vector to vi. So we get lambda I times vi. So we've checked that this matrix here has vi as an eigenvector, and lambda I is its eigenvalue. So the punchline of this is that a matrix A is said to be diagonalizable So diagonalizable if we can find a basis of eigenvectors, v1 up to vn, with eigenvalues lambda 1 up to lambda n, so that this matrix A is of this form, P, D, P inverse, where P is the matrix that we just made from the V's, the basis of eigenvectors, and D is the diagonal matrix with the eigenvalues along the diagonal. So we've seen some examples already of matrices that can be diagonalized, and we've seen some examples where they can't. So whenever you can find enough eigenvectors, whenever you can find a number of eigenvectors equal to the dimension that you're working in, n in this case, then your matrix is diagonalizable. But we also saw one example. We saw the matrix 1, I think I put an 8 there, 1, 0. So this matrix was not diagonalizable. It's a 2 by 2 matrix, but we only found a one-dimensional space of eigenvectors. We couldn't find 2 eigenvectors, we only found 1. So that's an example we've seen of a non-diagonalizable matrix. And a theme in linear algebra is whenever you're given a matrix, try to decide is it diagonalizable or not, and find a way to diagonalize it. Now, doing diagonalization by hand is often very tedious and a lot of work. Fortunately, computers are very good at crunching the numbers and doing this diagonalization process for you, but it's still important to understand what the computer is actually doing. It's finding a basis of eigenvectors so that you can write your matrix in this form. Right. Thank you for listening. That's all I have to say in this video.